June 20th, 1943. The morning sun glinted off the aluminum skin of a lone B-24 Liberator as it descended toward Rechlin airfield, approximately 100 kilometers northwest of Berlin. Captain Giovanni Raina, an Italian test pilot, carefully managed the 4 Pratt and Whitney radial engines, their distinctive oval nacelles containing a technological secret that German engineers were desperate to understand. Behind him sat 2 Italian mechanics, authorized passengers on this curious ferry flight from Munich. The bomber still wore its faded desert pink camouflage, an oddity against the green German countryside below. More oddly still, it bore Italian markings hastily painted over American stars, and a temporary Italian civil registration painted on the fuselage. This was Blonde Bomber 2, serial number 4123659, and it was about to become the Luftwaffe's window into a fundamental problem that no amount of German engineering excellence could solve. The problem wasn't the aircraft itself. By mid-1943, Luftwaffe fighter pilots had been engaging American B-24 seconds over occupied Europe for months. They understood the bomber's strengths and weaknesses, its ponderous handling at low altitude, its vulnerability to frontal attacks, its tendency to catch fire when hit. German pilots had learned to respect the .850 caliber machine guns bristling from the Liberator's turrets, and they'd witnessed the bomber's remarkable ability to absorb punishment and keep flying. But those observations, gleaned from frantic combat encounters at altitudes where oxygen masks fogged and machine guns jammed from the cold, couldn't reveal what German engineers needed to know. They needed to understand why American bombers consistently operated at altitudes where Luftwaffe interceptors struggled to reach them. They needed to know how the Americans had solved the fundamental problem of high-altitude flight. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. As Raina brought the massive bomber down onto Rechlin's runway, a group of Luftwaffe engineers and test pilots watched from the tarmac with intense professional interest. Among them was Hans-Werner Lersch, Rechlin's premier test pilot, a man who would fly 125 different aircraft types during the war without ever crashing or seriously damaging a single machine. Lersch had tested captured British Spitfires, American P-38s, Soviet Yak fighters. He understood Allied aviation technology intimately, but this B-24, with its peculiar engine installations and complex cockpit systems, represented something different. It represented a systematic approach to a problem that Germany had never fully solved, the problem of maintaining engine power in the thin air above 25,000 feet. The context of June 1943 makes this moment particularly significant. The combined bomber offensive was entering its decisive phase. American 8th Air Force, B-17 seconds and B-24 seconds were flying deeper into German-controlled airspace, with each passing week, striking industrial targets that German military planners had assumed were beyond the range of Allied heavy bombers. The Schweinfurt ball-bearing plants, the Regensburg Messerschmitt factories, the synthetic oil refineries at Ploesti, all suddenly vulnerable to daylight precision bombing. The raids came in massive formations, sometimes over 300 bombers, flying in defensive boxes designed to maximize interlocking fields of fire from their machine guns. And crucially, they came at altitudes between 20,000 and 28,000 feet, altitudes where German fighters faced a fundamental energy disadvantage. Luftwaffe doctrine in 1943 emphasized interception of bomber formations during their approach to the target, ideally catching them while still forming up or before they reached German airspace. The standard German interceptors, the Messerschmitt Bf 109 and the Focke-Wulf 190, were formidable aircraft. The Bf 109 G6, the most common variant in service by mid-1943, could reach 37,000 feet in theory. In practice, combat ceiling meant the altitude where an aircraft could still maneuver effectively, still turn, still climb to attack or dive to escape. For the Bf 109 G6, that combat ceiling was closer to 30,000 feet. Above that, the fighter became sluggish, its pilot struggling with thin air and temperatures that could drop to -50 degrees Fahrenheit. The FW190A series, powered by a BMW radial engine, faced similar limitations, though it maintained better handling characteristics at high altitude than the Messerschmitt. American B-24 seconds routinely operated at 25 to 28,000 feet. This wasn't merely preference, it was calculated strategy. At those altitudes, German fighters arriving to intercept them faced a critical energy deficit. A Bf-109 climbing to 28,000 feet to engage a B-24 formation consumed enormous amounts of fuel and time. Once there, the German pilot found his aircraft mushy, controls heavy, engine struggling. The American bombers, meanwhile, cruised comfortably, their pilots managing complex turbocharger systems that maintained sea-level manifold pressure in air thin enough that a man without oxygen would lose consciousness in seconds. The turbocharger was not a mystery to German engineers in June 1943. German aviation pioneers had experimented with exhaust-driven superchargers since the early 1920s. The concept was straightforward in principle. Use waste exhaust gases, energy the engine was throwing away, to spin a turbine. Connect that turbine to a compressor. Use the compressor to ram dense air back into the engine's intake manifold. The engine, fed artificially dense air, produces power as if flying at sea level, even though the aircraft is at 30,000 feet, where atmospheric pressure is only 1/3 of sea level pressure. It was elegant engineering, recovering energy that would otherwise blast uselessly out the exhaust pipes. But understanding a principle and implementing it in operational aircraft are vastly different challenges. German engineers had pursued a different solution to the altitude problem: mechanical superchargers driven directly from the engine's crankshaft. These were simpler, more compact, more reliable. They also stole horsepower from the engine to run themselves, and they had hard altitude limits. A mechanical supercharger could maintain pressure to perhaps 35,000 feet under ideal conditions, but the performance fell off rapidly above that. More critically, mechanical superchargers required the aircraft designer to choose a specific critical altitude where the supercharger worked most efficiently. Design it for 20,000 feet, and performance at 30,000 feet suffered. Design it for 30,000 feet, and takeoff power at sea level was compromised. The Americans had chosen the turbocharger path, accepting its complexity, weight, and maintenance demands in exchange for flexibility and performance. Every B-24 Liberator carried 4 General Electric Type B-22 turbochargers, one mounted in each of those distinctive oval engine nacelles. Each turbocharger weighed approximately 360 pounds and spun at speeds up to 21,000 revolutions per minute, nearly twice the engine's own crankshaft speed. At those velocities, precision manufacturing was critical. Any imbalance, any debris in the exhaust stream, any microscopic flaw in the turbine wheel, and the unit could disintegrate catastrophically, sending shrapnel through the nacelle and potentially igniting the fuel tanks housed in the wings. The engineering challenges didn't stop with the turbocharger itself. Exhaust gases from the 14-cylinder Pratt and Whitney R1830 radial engines reached temperatures exceeding 1600 degrees Fahrenheit. Channeling those gases from the engine's exhaust ports to the turbine, located aft in the nacelle, required heavy steel ducting capable of withstanding sustained extreme temperatures without warping or cracking. Then came the intercooler problem. When you compress air, basic thermodynamics dictates that you heat it. Compressed air is hot air. Hot air is less dense. Feed hot compressed air into the engine, and you've defeated the entire purpose of the turbocharger. The solution was an intercooler, a heat exchanger that used outside air to cool the compressed charge before it entered the engine's intake manifold. On the B-24, this intercooler was integrated into the distinctive oval nacelle shape, using carefully designed ducting to route cooling air around the turbocharger installation. Pilots managed this entire system through a complex arrangement of controls and instruments. Each engine had its own turbocharger regulator, manually adjusted via controls on the cockpit pedestal between the pilot and co-pilot. The pilot set a desired manifold pressure based on altitude and power requirements, The turbocharger wastegate automatically adjusted to maintain that pressure, varying the amount of exhaust gases flowing through the turbine. Too little wastegate opening and boost pressure could exceed safe limits, potentially destroying the engine. Too much, and power dropped off. Managing 4 independent turbocharger systems, along with mixture controls, propeller pitch, and engine synchronization, while flying in tight formation through flak and fighter attacks, demanded extraordinary concentration and skill. This was the system that Captain Raina had flown from Munich to Rechlin, and it was this system that Hans-Werner Lerche and his fellow German test pilots needed to understand, not merely understand in abstract technical terms, but understand operationally. Could German pilots be trained to intercept B-24 seconds effectively given the aircraft's high-altitude performance? Were there tactical vulnerabilities the turbocharger system created? Most importantly, could Germany adapt the technology for its own aircraft? The capture of Blonde Bomber 2, 4 months earlier, had been pure chance. Second Lieutenant Don Story and his crew from the 98th Bomb Group, the Pyramiders, had participated in a raid against Naples on February 20th, 1943. The Liberator took flak damage over the target, wounding 1 crew member and damaging fuel systems. Disoriented, low on fuel, Story made a desperate navigation error. Looking desperately for Malta, he instead spotted what he believed was a friendly airfield. It was Pacino, Sicily, firmly in Italian hands. The B-24 landed safely. Italian soldiers quickly surrounded the aircraft. The crew, expecting friendly reception, instead found themselves prisoners. The Italians immediately recognized the intelligence value of an intact, relatively undamaged American heavy bomber. The Regia Aeronautica, Italy's air force, transported Blonde Bomber 2 to Catania Fontanarossa, then to Guidonia, the Italian test and research center near Rome. Italian engineers conducted preliminary examinations, but they lacked the industrial infrastructure and technical expertise to fully evaluate the sophisticated American systems. The Germans wanted the aircraft. Diplomatic negotiations between Axis partners led to an agreement. Italy would loan the B-24 to Germany for detailed evaluation at Rechlin. Captain Raina's June 20th ferry flight was the culmination of those negotiations. The bomber had been in Italian hands for 4 months, enough time for Italian engineers to conduct basic testing and familiarize themselves with the aircraft systems. Now it was Germany's turn. The Luftwaffe planned comprehensive evaluation, flight testing to determine performance characteristics, detailed examination of the turbocharger installation, analysis of armament, structure, and systems. They particularly wanted to understand the automated engine management systems that allowed American pilots to focus on formation flying and target acquisition rather than constant manual adjustment of engine parameters. As Raina shut down the 4 Pratt and Whitney engines on the Rechlin ramp, German ground crew immediately surrounded the bomber, securing it, beginning preliminary documentation. The aircraft would be assigned the Luftwaffe designation T9+FK, the coding used by Zirkus Rosarius, the test unit at Rechlin. Large German crosses would soon be painted on the fuselage and wings, and the entire aircraft would eventually be repainted from its desert pink camouflage to an inconspicuous dark green, the pin-up nose art of the blonde woman carefully painted over with vigorous brush strokes, but all that would come later. First, the Germans needed to understand what they had captured. Lerche began his familiarization immediately, spending hours in the cockpit studying the instrument panel, operating controls, trying to infer function from form. The B-24 cockpit was, in his later published recollection, bewilderingly complex compared to German fighters he knew intimately, twice the number of gauges, strange levers controlling systems he'd never encountered. Most puzzling were the turbocharger controls themselves, 4 separate regulators that somehow maintained manifold pressure automatically through changes in altitude. German engines required constant manual adjustment of throttle and mixture. The B-24's engine management appeared partially automated, a sophistication that suggested American aviation had moved beyond German assumptions about operational aircraft design. The first flight would be critical. Lerche needed to understand not just whether the B-24 flew, but how it flew. Could he safely operate the turbocharger system without benefit of pilot's manual or formal training? Were there hidden quirks or dangerous characteristics? Most importantly, how would the aircraft perform at altitude, where its turbochargers provided the decisive advantage American pilots exploited every day over German airspace? But first, they needed to start the engines. The Pratt and Whitney R-1830 start sequence itself revealed American design philosophy. Unlike German inline engines with their sharp bark at startup, the radial produced a deep rumble as its 14 cylinders fired in sequence. Each engine required methodical procedure, priming, magneto checks, careful monitoring during warm-up. Lerche followed the sequence meticulously, his engineer's mind cataloguing each step, inferring purpose. When all 4 engines were running smoothly, their propellers creating a distinctive harmonic beat as they synchronized, Lerche began taxi trials, getting the feel for the aircraft's size, its nose-wheel tricycle landing gear so different from the tail-dragging configuration of every German bomber he'd flown. The B-24 was massive. At 64 feet long, with a wingspan of 110 feet, it dwarfed the German Heinkel, He-111 and Dornier Do-17 bombers Lerche knew well. Empty weight of 32,600 pounds, maximum takeoff weight exceeding 60,000 pounds. This wasn't merely a heavy bomber. It was a flying industrial artifact representing production capacity and material resources that Germany, strained by fighting on multiple fronts, could barely imagine, let alone match. The Davis wing that gave the B-24 its distinctive high-shoulder configuration was an engineering triumph and a tactical liability. Designed by aeronautical engineer David Davis, the wing featured high aspect ratio, long span but relatively narrow chord, optimized for efficient cruise at high altitude. It generated less drag than conventional wings, allowing higher speeds and longer range. But it was also unforgiving. At low speeds, particularly during landing approach, the wing gave little warning before stalling, and the wing's narrow chord and lightweight stressed skin construction made it vulnerable to battle damage. German pilots had learned that concentrated fire into the wing's fuel-filled center section could bring down a B-24 quickly, the fuel system lacking the self-sealing integrity of later model aircraft. But all this was academic knowledge gained from combat reports. Lerche needed to experience it himself. By the end of June 1943, he felt prepared for the first flight. The test would be methodical, climbing to altitude while carefully monitoring engine parameters, testing handling characteristics at various speeds and altitudes, evaluating the turbocharger system's automatic regulation. Weather was favorable. Rechlin cleared the airspace. Ground crew stood ready with fire equipment, understanding the risks of testing an unfamiliar aircraft whose systems they didn't fully understand. Lerche advanced the throttles. 4 Pratt and Whitney engines responded with smooth power. The B-24 accelerated down Rechlin's runway, its tricycle landing gear making takeoff vastly simpler than the tail-dragging German bombers whose tendency to ground loop during takeoff roll had killed numerous pilots during training. At flying speed, Lerche rotated the nose smoothly upward. The Liberator lifted off, climbing away from Rechlin on a northerly heading. Immediately, Lerche understood what made the B-24 operationally significant: power. The 4 R-1830s produced 1,200 horsepower each at takeoff, 4,800 total horsepower pushing 60,000 pounds of aircraft, fuel, bombs, and crew into the sky. But more significantly, as the aircraft climbed through 10,000 feet, then 15,000, then 20,000, the power didn't fade. The turbochargers were working automatically, maintaining manifold pressure, allowing the engines to breathe as if still at sea level. At 25,000 feet, where a Bf-109's engine would be producing less than 60% of its sea level power, the B-24's engines hummed with almost undiminished output. Lerche tried various maneuvers, gentle turns, climbs, descents, speed variations. The B-24 handled exactly as its reputation suggested. At low speeds, it was ponderous, requiring heavy control inputs. Formation flying would be demanding, requiring constant throttle and trim adjustments, but in clean, high-speed cruise configuration at altitude, it was stable, solid, predictable. Most importantly, at 28,000 feet, it still had energy to maneuver, energy to maintain formation, energy to maintain defensive fire from its 10-50 caliber machine guns while flying deeper into Germany than German strategic planners had believed possible for Allied heavy bombers. The turbocharger system's sophistication impressed Lerche profoundly. German fighters relied on emergency boost systems, methanol water injection that provided brief power surges at the cost of severe engine stress and limited duration. The B-24's turbos provided sustained high-altitude power, limited only by fuel capacity. An American bomber formation could cruise at 28,000 feet for hours, their pilots monitoring gauges but not requiring constant manual intervention to maintain engine performance. German interceptors climbing to engage them faced accumulating fatigue, both mechanical and human, as pilots struggled with thin air, extreme cold, and engines producing progressively less power as altitude increased. What Lerche couldn't fully appreciate during his test flights was the industrial context that made the B-24's turbocharger system operationally viable. Each B-24 required 4 precision turbochargers manufactured to tolerances that required advanced machine tools and quality control procedures. Multiply that by 18,500 aircraft, the total B-24 production during the war, and you're discussing 74,000 turbochargers, each one a precision instrument spinning at 21,000 RPM in an environment of extreme temperature and vibration. Germany's aviation industry, already strained by Allied bombing and chronic shortages of strategic materials like chromium and molybdenum needed for high-temperature alloys, could not have produced turbochargers at the scale required, even if German engineers had perfected the design. The summer of 1943 was a period of mounting crisis for the Luftwaffe. While Lerche conducted his flight trials with Blonde Bomber 2 at Rechlin, German fighter squadrons across occupied Europe faced an increasingly difficult tactical situation. American bomber formations were growing larger and more sophisticated. The combat box formations that USAAF commanders had developed, pioneered by Colonel Curtis LeMay of the 305th Bomb Group, created interlocking fields of defensive fire that made traditional German fighter tactics increasingly costly. A standard 8th Air Force wing formation consisted of 54 B-17 seconds, or B-24 seconds, flying in a defensive box approximately 7,000 feet deep, 2,000 feet wide, and spread 3,000 feet vertically. Each bomber mounted up to 10 50 caliber machine guns. A 54 plane box could theoretically bring 700 heavy machine guns to bear against attacking fighters. German fighter pilots had learned through brutal experience that frontal attacks offered the best chance of success. The nose of early B-24D models was the weakest point in the defensive armament, protected only by hand-held flexible guns operated by the bombardier and navigator. But frontal attacks required precise timing, closing speeds that exceeded 600 miles per hour, and nerves that could hold steady, while flying directly at a formation of bombers whose concentrated fire could shred a fighter in seconds. Many German pilots, particularly newer replacements with limited training, broke off their attacks prematurely or fired from too great a range. Those who pressed home their attacks often found themselves committed to a dive through the entire bomber formation, running a gauntlet of defensive fire from multiple aircraft. The altitude problem compounded these tactical challenges. A Bf-109 climbing to 28,000 feet to intercept a B-24 formation consumed approximately 25 minutes from takeoff. During that climb, the fighter burned fuel at a high rate, leaving limited time on station for actual combat. Once at altitude, the fighter's performance was degraded. Control surfaces felt mushy, turn rates decreased. Climb rate dropped to perhaps 500 feet per minute, compared to over 3,000 feet per minute at sea level. Most critically, if the German pilot made a firing pass and then had to dive away to escape defensive fire, Regaining altitude for a second attack required several minutes of fuel-burning climb, during which the bomber formation continued toward its target. American bomber crews understood these dynamics. Their standard operating procedure when under fighter attack was to maintain tight formation, maximize defensive fire, and continue toward the target. Breaking formation meant isolation, vulnerability, and near-certain loss. But staying in formation meant accepting that some aircraft would be hit, some crew members would be wounded or killed, and the formation would keep flying. It was industrial warfare in its purest form. The side that could accept losses, replace aircraft and crews, and continue operations would eventually overwhelm the side that could not sustain the exchange rate. By July 1943, after multiple test flights, Lerche had developed a comprehensive understanding of the B-24's characteristics. His reports documented performance data: maximum speed of 300 miles per hour at 30,000 feet, and service ceiling of 28,000 feet, though the aircraft remained controllable above that altitude. Initial climb rate of approximately 1,000 feet per minute at maximum takeoff weight. Range of 1,700 miles with a 5,000-pound bomb load, extendable to over 3,000 miles with reduced bomb load and maximum fuel. These figures confirmed what German intelligence had already estimated from combat observations. The B-24 was slower than the B-17, but had superior range. It was more difficult to fly in formation, particularly in turbulence, but carried a heavier bomb load. The detailed technical evaluation, however, revealed information that no amount of external observation could provide. German engineers at Rechlin methodically examined every system, taking detailed measurements, photographing components, attempting to reverse engineer American design decisions. The turbocharger installation received particular attention. Engineers measured ducting dimensions, examined intercooler design, studied the automatic wastegate mechanism. They discovered that General Electric, the turbocharger manufacturer, had achieved remarkable precision in turbine wheel balance. The unit could spin at 21,000 RPM for hours without vibration, significant enough to cause structural fatigue. This level of manufacturing precision suggested machine tool capabilities and quality control procedures that German industry would struggle to match under wartime conditions. The automatic engine management systems fascinated German engineers who were accustomed to aircraft that required constant manual adjustment. The B-24's constant-speed propellers, manufactured by Hamilton Standard, automatically adjusted blade pitch to maintain selected RPM regardless of power setting or airspeed. This allowed pilots to set RPM once, during climb, and then largely ignore propeller management unless changing power settings dramatically. German aircraft used similar constant-speed propellers, but the American implementation appeared more refined, more reliable, less prone to failure. Similarly, the turbocharger regulators maintained manifold pressure automatically, requiring only occasional adjustment as altitude changed. A German pilot flying a Bf-109 at high altitude made constant small throttle adjustments to maintain power as air density changed. An American B-24 pilot set desired manifold pressure and let the turbocharger regulator do the work. These differences seem minor in isolation, but multiply them across hours of high-altitude formation flying, add the stress of combat, the cold at -50 degrees Fahrenheit, the oxygen deprivation that affects judgment even with supplemental oxygen, and the cumulative effect was significant. American bomber crews could focus more attention on navigation, target acquisition, and defensive tactics because their aircraft systems demanded less moment-to-moment attention. German fighter pilots, meanwhile, divided their attention between flying, fighting, and constant engine management. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The structural examination revealed both strengths and vulnerabilities. The B-24's fuselage was a semi-monocoque design, load-carrying skin supported by internal frames and stringers. This construction method was lighter and more efficient than the heavier framed structures common in German bombers, but it also meant that battle damage could compromise structural integrity more quickly. The Davis wing's lightweight construction made it particularly vulnerable. German engineers noted that the wing's fuel tanks, though self-sealing in later models, occupied much of the wing's internal volume. Concentrated fire into the wing could puncture multiple tanks, and the resulting fuel leak could quickly become catastrophic if ignited by tracer rounds or hot engine parts. The defensive armament impressed German evaluators less than the turbocharger system. 10 50 caliber Browning M2 machine guns represented formidable firepower, but German engineers noted limitations. The powered turrets, particularly the Sperry ball turret mounted in the belly, had restricted fields of fire and mechanical complexity that made them vulnerable to malfunction. The handheld flexible guns in the nose were difficult to aim accurately during evasive maneuvers. Most significantly, the guns were air-cooled, which meant sustained firing could cause overheating and jams. German cannon armament, particularly the 20mm MG-151 and 30mm Mk-108, had superior destructive power per round, though lower rates of fire. What German engineers ultimately concluded was that the B-24 represented a fundamentally different design philosophy. German aviation emphasized performance optimization, technical excellence in specific parameters. Each German aircraft design pushed the envelope in particular ways. The Messerschmitt 163 rocket interceptor achieved phenomenal rate of climb. The Heinkel He 177 featured remote-controlled defensive turrets. The Focke-Wulf TAR 152 operated effectively at extreme altitudes with pressure cabin. But these aircraft were produced in limited numbers, required extensive specialized training, and often suffered reliability problems. The B-24, by contrast, accepted compromises in individual performance parameters to achieve operational reliability at scale. It wasn't the fastest bomber, the highest flying bomber, or the most heavily armed bomber, but it was fast enough, flew high enough, carried adequate armament, and most critically, could be produced in enormous quantities by semi-skilled workers using production line, the techniques pioneered by American automotive industry. The Ford Motor Company's Willow Run plant, which would eventually produce B-24 seconds at a rate exceeding 1 aircraft per hour during peak production, represented industrial capacity that Germany simply could not match. This was the fundamental insight that German evaluation of Blonde Bomber 2 provided, though it was an insight that German military leadership was reluctant to fully accept. The problem wasn't that German engineers couldn't understand American technology. They understood it quite well. The problem was that understanding the technology and possessing the industrial infrastructure to implement it at scale were entirely different challenges. Germany in mid-1943 was fighting on multiple fronts, conducting offensive operations in the Soviet Union, defending against Allied bombing, maintaining occupation forces across Europe, and attempting to keep pace with an arms race that required constant innovation just to maintain parity. The resources required to retool German aviation industry to produce turbocharger-equipped aircraft at the scale the B-24 represented simply didn't exist. During one of the later test flights at Rechlin, disaster struck. On what would be approximately the 4th evaluation flight, Lerche brought Blonde Bomber 2 in for landing after a routine high-altitude performance test. The approach was normal, the touchdown smooth, but as the nose wheel made contact with Rechlin's grass runway, something failed. The nose gear strut collapsed, and the bomber's nose dropped abruptly to the ground. The propellers struck the earth, their blades bending and shattering. The aircraft skidded to a halt in a cloud of dust and torn grass, its nose crumpled, structural damage evident. The crew was uninjured, but Blonde Bomber 2 was grounded indefinitely. The nose gear failure might have been metal fatigue from combat damage sustained during the February raid on Naples. It might have been wear from the months of testing and ferry flights between Italian and German facilities. Or it might simply have been bad luck, a component failure that could happen to any aircraft. Whatever the cause, the result was clear. Extensive repairs would be required before the aircraft could fly again. The landing gear assembly would need to be rebuilt or replaced. The nose structure required straightening, the propellers needed replacement, and replacement propellers for Pratt and Whitney engines were not exactly abundant in German-controlled territory. The repairs took weeks. By early September 1943, Blonde Bomber 2 was flying again, though now wearing a new paint scheme. The desert pink camouflage that had made it conspicuous over European landscapes had been replaced with overall dark green, a colour that would blend better with German forests and farmland. The nose art, the smiling blonde woman that had given the aircraft its name, had been painted over completely, erased by German ground crew who had no use for American pin-up imagery. The aircraft now wore German crosses on fuselage and wings, and yellow identification bands on wing undersurfaces and tail surfaces, the standard Luftwaffe practice for captured aircraft to prevent friendly fire from German anti-aircraft units. But even as Blonde Bomber 2 returned to flight status, its relevance was diminishing. The Luftwaffe now had multiple captured American bombers available for evaluation. Additional B-24 seconds had been captured after crash landings or mechanical failures over occupied territory. B-17 Flying Fortresses, the other mainstay of the American strategic bombing campaign, were also available for testing at Rechlin. The initial excitement of examining a completely intact example of American heavy bomber technology had given way to the sobering realization that understanding the technology didn't provide a path to countering it effectively. The tactical situation over Europe continued to deteriorate for the Luftwaffe through the autumn of 1943. October saw particularly heavy losses during American raids on Schweinfurt and Regensburg. The Americans were learning to time their raids to maximize the duration escort fighters could remain with the bomber formations. Drop tanks extended the range of P-47 Thunderbolts, allowing them to penetrate deeper into German airspace before having to turn back. The Lockheed P-38 Lightning, with its twin-engine design and substantial fuel capacity, could escort bombers even farther. And on the horizon loomed the North American P-51 Mustang, a fighter that would eventually escort bombers all the way to Berlin and back, fundamentally changing the air war's dynamics. German response to the bombing campaign evolved through trial and error. Frontal attacks by heavily armed fighters became standard doctrine. The Bf 109G6 received additional cannon armament, sacrificing some performance for increased firepower. Specialized bomber-destroyer variants like the twin-engine Messerschmitt 2-10 and the rocket-armed Messerschmitt 163 were developed to attack bomber formations from angles and altitudes that minimized exposure to defensive fire. But none of these innovations addressed the fundamental problem. American bomber formations operated at altitudes where they held inherent advantage, and German fighters climbing to intercept them faced energy deficit that tactical skill alone couldn't overcome. The wild sow, or wild boar, night fighting tactics introduced in summer 1943 represented one attempt to adapt. Single-engine day fighters, traditionally considered unsuitable for night operations, were pressed into service against RAF Bomber Command's night raids. Operating above the altitude ceiling of German anti-aircraft fire, these fighters attacked bombers, illuminated by searchlights and the glow of fires on the ground. The tactic achieved some initial success, particularly during the devastating raids on Hamburg in July and August 1943. But wild sow operations were dangerous, requiring pilots to fly in darkness without radar assistance, often in poor weather conditions. Accident rates were high, and by spring 1944, improved British jamming of German radar and the introduction of more sophisticated night fighter equipment made wild sow obsolete. By late 1943, Blonde Bomber 2 had been transferred from Rechlin to Kampfgeschwader 200, KG 200, one of the Luftwaffe's most secretive units. KG 200 operated captured Allied aircraft for special missions, long-range reconnaissance flights over Allied territory, supply drops to German forces operating behind enemy lines, and occasionally infiltration missions where German aircraft in Allied markings attempted to shadow Allied bomber formations to gather intelligence. The B-24, with its long range and ability to blend into American formations if painted appropriately, seemed ideal for such operations. But operational use of captured aircraft presented enormous challenges. Maintenance was a constant problem. American replacement parts were obviously unavailable in Germany. German mechanics had to fabricate parts or cannibalize components from other captured aircraft. Engine maintenance was particularly difficult. The Pratt and Whitney R-1830 engines required specific lubricants, spark plugs, and maintenance procedures that German ground crews had to learn through experimentation. The turbocharger systems, complex even when maintained by trained American mechanics with proper tools and parts, became increasingly unreliable under German operation. Documentation was another challenge. Unlike the B-17, which the Luftwaffe had captured in sufficient numbers to develop comprehensive technical manuals in German, the B-24 remained relatively rare in German hands. Pilots and crews operating captured Liberators relied on partial translations of American manuals, notes from test pilots like Lerche, and institutional knowledge passed between crews. This informal training system worked adequately for experienced pilots, but was dangerous for less skilled airmen. The strategic bombing campaign's intensity continued to increase through 1944. By spring, American 8th Air Force could launch raids of over 800 bombers, escorted by fighters that now ranged freely over German airspace, seeking combat with Luftwaffe interceptors. The Germans called it Big Week, 6 days in February 1944, when American bombers struck aircraft factories across Germany in coordinated maximum effort raids. The Luftwaffe lost over 300 fighters during Big Week, not merely aircraft but experienced pilots whose training and combat experience couldn't be quickly replaced. Replacement pilots arriving at frontline units often had minimal flight training, sometimes less than 100 hours total flying time. They were lambs being sent to slaughter, facing American fighter pilots with hundreds of combat hours in aircraft that held performance advantage across most of the flight envelope. The specific fate of Blonde Bomber 2 after its assignment to KG-200 is somewhat unclear in historical records. Captured aircraft operated by KG-200 were deliberately kept secret, with minimal documentation to prevent intelligence leaks. What is known is that the aircraft survived until the end of the war. American forces advancing into Germany in April and May 1945 discovered Blonde Bomber 2 at Rechlin, heavily damaged by strafing attacks from American fighters who had caught it on the ground. The airfield had been repeatedly bombed and strafed as Allied forces closed in on Berlin. Most of the captured Allied aircraft that KG-200 had operated were destroyed during these final attacks, either by direct hits or deliberately burned by retreating German personnel to prevent recapture. The bomber's American crew, Second Lieutenant Don Story and his men, had been captured when they landed at Pacino in February 1943. They spent the remainder of the war in Italian and German prisoner-of-war camps, enduring harsh conditions but ultimately surviving. When Italy surrendered in September 1943, some Allied prisoners attempted escapes during the chaos of Italian capitulation and German occupation. Story's crew attempted to evade capture by German forces, but were eventually recaptured. They were transferred to German camps, first Stalag Luft 3, later to other facilities as German forces retreated westward in the war's final months. They were liberated by Allied forces in spring 1945 and returned to the United States, their war over, their aircraft a burnt wreck on a German airfield they would never see. Hans-Werner Lerche survived the war with his remarkable safety record intact, 125 different aircraft types tested, 0 crashes. After Germany's surrender, Allied intelligence services extensively debriefed him about German aircraft development programs and captured Allied aircraft evaluations. His memoirs, published in 1977 in German and translated to English in 1980, provide invaluable first-hand accounts of German aviation technology assessment. His observations about the B-24's turbocharger system were professional, technical, and grimly realistic about Germany's inability to match American industrial capacity. The broader strategic lesson that emerged from the German evaluation of captured B-24 seconds was uncomfortable but undeniable. By mid-1943, the outcome of the air war over Europe was being determined not by pilot skill, tactical innovation, or even aircraft performance in narrow technical terms, but by industrial capacity applied at national scale. The United States could design adequate equipment and produce it in overwhelming quantities, while simultaneously producing everything else a modern military required. Germany, fighting on multiple fronts against opponents whose combined industrial capacity exceeded German capacity by factors of 5 or more, simply could not compete in a war of industrial attrition. The B-24 Liberator's turbocharger system represented this disparity in microcosm. Each aircraft required 4 precision turbochargers, each one a complex mechanism requiring advanced metallurgy, precision machining, and quality control procedures that Germany's strained industrial base could barely maintain even for existing equipment, let alone new production. Multiply those requirements by 18,500 aircraft, add the spare parts pipeline, the training programs, the maintenance infrastructure, and you're describing an industrial undertaking that required resources Germany no longer possessed by 1943. German engineers at Rechlin understood this. They could examine Blonde Bomber 2's turbochargers, measure clearances, analyze metallurgy, reverse engineer control systems. They could write detailed technical reports documenting every aspect of the American design, but that knowledge couldn't produce the chromium needed for high-temperature turbine blades. It couldn't produce the precision machine tools required to manufacture turbine wheels to tolerances measured in thousandths of an inch. It couldn't produce the electrical generators, the factories undamaged by bombing, the skilled workforce not conscripted into military service, the rail network still functioning to transport materials and components. The altitude advantage that turbochargers provided American bombers was ultimately an expression of industrial capacity. Not merely the capacity to design sophisticated technology, but the capacity to produce it at scale, maintain it in field conditions, and replace it when damaged or worn out. German fighter pilots climbing to 28,000 feet to intercept. B-24 formations faced not merely the tactical challenge of altitude disadvantage, they faced the material expression of an industrial system that could simultaneously produce 20,000 heavy bombers, 15,000 escort fighters, millions of tons of bombs, billions of rounds of ammunition, and still maintain the civilian economy, feed the population, and conduct research into even more advanced weapons systems. By early 1945, as Allied armies closed in on Germany from east and west, the Luftwaffe was flying fighters without adequate fuel, flown by pilots with minimal training, defending factories that had already been bombed into rubble. Blonde Bomber 2, sitting damaged on Rechlin's cratered runway, represented a lesson learned too late to matter. The lesson arrived with perfect clarity, documented in thousands of pages of technical reports, understood completely by German engineers who could see exactly how the Americans had solved problems that Germany faced. But knowledge without resources is merely academic understanding. The industrial mathematics that determined warfare's outcome in the 20th century proved immune to tactical brilliance or technical excellence constrained by material scarcity. American bomber crews who flew B-24 seconds over Europe in 1944 and 45 probably never thought about the turbochargers that allowed them to operate at 28,000 feet. The system worked automatically, requiring minimal pilot input, reliable enough that crews trusted it with their lives every mission. That invisibility, that reliable operation of complex technology, represented American industrial maturity. The most dangerous weapon in America's arsenal wasn't any individual technology, however impressive. It was the complete industrial system that could conceive, design, develop, test, produce, and logistically support thousands of complex weapons systems simultaneously, while maintaining quality and continuously improving designs based on combat experience. The captured B-24 seconds at Rechlin taught this lesson with undeniable clarity. German engineers measured it precisely, documented it professionally, reported it accurately through their chain of command. The lesson arrived too late to change anything. By the time Blonde Bomber 2 was being meticulously examined at Rechlin in summer 1943, the outcome of the war was already determined by industrial mathematics that no amount of German engineering skill or pilot courage could overcome. The Liberators sitting on German airfields wearing hasty crosses over American stars represented a future that had already arrived, one in which industrial capacity had become the decisive factor in modern warfare. The turbochargers that made interception impossible weren't merely mechanical devices spinning in engine nacelles. They were manifestations of a complete industrial ecosystem, an economy capable of producing precision machinery at scale, of training workers to manufacture components to exacting tolerances, of maintaining supply chains across oceans, of replacing losses faster than they accumulated. German engineers understood the turbochargers perfectly. What they couldn't replicate was the America that produced them. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.